In this part, we will discuss thioethers and epoxides. Previously, we talked about ethers, their reactions, and their methods of prep. What are thioethers? Thioethers are usually analog of ethers. So instead of having ROR, we have an RSR. So that's what we see in thioethers, or what we call sulfides. The naming will be similar to how we name ethers. If I have an ROR, the common name would be basically dialkyl ether, or alphabetically list the first alkyl and then the second, and then end the name with ether. Here will be similar. So it will be basically dialkyl sulfide. Like in this case, for example, we have two methyl groups attached to a sulfur. So that's a dimethyl sulfide. If I have two different alkyl groups, again, this is a common name. What would the name be? Would be methylphenyl sulfide. How would the IUPAC name be? Well, in the ether, we consider the ether group as an alkoxy, as a substituent. So here would be an alkyl thio, that will be the substituent. So methylthiobenzene would be the IUPAC name of this structure. How about this? What do we have? We have basically an alkene. So the alkene gets a priority over the sulfur. So the alkene would be basically had to be numbered along with the chain, and the sulfur moiety will be the substituent. So what do I have? I have a methyl and I have an ethyl thio. So two substituents, a methyl and an ethyl thio. So 1, 2, 3, 4, 5. So now we know that we have a methyl on carbon number 2, and we have an ethyl thio on carbon number 4. So the alphabetical order will be 4 ethyl thio, 2 methyl, pent, 2 ene. Recognizing that the alkene unit is actually on carbon number 2. There's no E or Z here due to the fact that the two groups are the same on one side of the alkene. RSH has a more acidic hydrogen compared to an ROH. So the pKa, we're talking about SH that has about 10. pKa of an alcohol is about 16. So the more acidic the hydrogen, that's easier actually to be abstracted. So therefore, generating a thiolate will be an easy task. So what do we do with that? Well, similar to alkoxide, what did we use them for? They are used as bases, and they are also used as strong nucleophiles. So if I have alkyl halide or alkyl tosylate or alkyl mesylate, it will basically do an SN2 substitution, and that will give me basically the nucleophilic substitution outcome. Now, S minus, due to the fact that you have a stronger acid, SH corresponding structure, S minus will be a weaker base compared to alkoxides. So that's important to keep in mind. So you won't find thiolates being used as bases. They are usually used as strong nucleophiles only. And this example, we see here that the S minus attacks CX. It's an SN2 pathway. I have a primary alkyl halide, so that's going to give me basically the ethyl propyl sulfide. And that's how we make sulfides. We generate a thiolate from a thiol, and we attack an RX to end up getting the sulfide structure. Sulfide reactions, we can do oxidation to generate useful compounds such as DMSO. We see in DMSO as an example of a polar A product solvent. So we have dimethyl sulfide being oxidized. H2O2, acetic acid will be the oxidation condition, and that will basically insert a sulfonyl group. And if I have another oxidation method of the sulfoxide, I will end up making basically the sulfones. So the level of oxidation, just similar to alcohol, getting to an aldehyde versus carboxylic acid. Well, here sulfides are usually oxidized to a sulfoxide, and then the sulfoxide will be oxidized to the sulfone. Other reactions, if I start with the dimethyl sulfide or a dialkyl sulfide and I do methylation or alkylation, I end up making basically what we call a sulfonium salt. So dimethyl sulfide, the sulfur has two lone pairs. One of them will attack the CH3 kick off the eye, and that will give you basically this structure. What do we use this for? Usually are used as alkylating agent. So that's what the use of the sulfonium salt. Where did we see dimethyl sulfide in the reaction that we have learned in this course? We've seen it in oxidative cleavage of alkenes, and to be more specific, ozonolysis. So the first step was O3, and that will basically generate an ozonide. And this ozonide will have to collapse to give you the dicarbonyl moiety. We do that with a reducing agent that is dimethyl sulfide. So they are easily oxidized. That's why they are usually used as reducing agents. So they are easily oxidized, and that's why they are used as mild reducing agent. And this dimethyl sulfide will generate dimethyl sulfoxide. Similar to thioethers, we have the silyl ethers, but silyl ethers usually are used as protecting groups. Now, what is a silyl ether? So if I look at the ether compound, it's an ROR prime. Thioether would be an RSR prime, which is a sulfide. Silyl ether would be an RO silyl R prime, R prime, R prime. So I have basically 4 bonds around the silyl. One of them is attached on oxygen, and that would make it a silyl ether compound. What do we use those for, the silyl ethers? First of all, they are resistant to some acids, bases, and oxidizing agents. And they are easily formed and easily deprotected or hydrolyzed. So here's an application of silyl ether. The fact that they are easily put, easily removed. If I have this reaction taking place, I have a structure that has an alcohol and a carbonyl reacting with a Grignard reagent. Well, I know that Grignard will do nucleophilic addition to a carbonyl. So my goal would be having the phenyl attacking the carbonyl carbon, opening that up and making alcohol at the end, hoping that this will be the one that's going to be formed. But well, guess what? That's not going to happen. Why? Because Grignard reagent is also a basic reagent. So it's going to look for that OH and it's going to think of the abstraction of the hydrogen rather than doing a nucleophilic addition. So the abstraction of the OH will basically kill the reaction and will prevent the Grignard reaction from happening. How do we go around this? Because my interest is to make this structure. Well, here's the way to do it. I take the alcohol, I protect it with a silyl halide. So in this case is the chlorotriisopropylsilane. So, or the abbreviation for it is TEPS chloride, TEPS chloride. Once we react this with the alcohol in presence of triethylamine for the purpose of neutralizing the resulting HCl, we end up making the silyl ether. And you can see here clearly the isopropyl group and the silyl attached on oxygen. So that's the silyl ether. I do the chemistry that I want, which is the Grignard. And then what do I do at the end? I get rid of the silyl group by simply treating it with TBAF, tetrabutyl ammonium fluoride, TBAF. And that will basically deprotect the TEPS group. So that's how important it is actually to have an option in case of some candidates that I need actually to do some chemistry on, but I get distracted because of other functional group that will prevent you from doing so, such as this example right here. So how would I do this chemistry then? I will have to basically protect the OH, and once I protect it with the TEPS chloride and presence of triethylamine, I have the silyl ether, I do the Grignard, and then I treat the reaction with TBAF to get this structure at the end, which is the alcohol, the diol actually at the end. Here's an application of the sulfonium salt that we made out of the dimethyl sulfide or the dialkyl sulfide. So having a nucleophile reacting with the sulfonium salt will simply attack the R group and kick off the sulfur, and that will basically give you the nucleophilic substitution outcome plus the sulfide, which I can go back and alkylate, get the sulfonium salt, and keep doing the chemistry until I'm actually done with whatever I want to get in terms of alkylation. So here's an example. I have pyridine reacting with a sulfonium salt. What do I have? I have a nitrogen lone pair that's going to attack the methyl, and I'm going to end up making basically an N-methyl pyridinium iodide. Those ammonium salts usually are used as antibacterial. They could be used as antifungal sometime as well. So that's a way how to make basically ammonium salts. Plus the dimethyl sulfide would be the side product. Epoxides. We've seen this moiety being made from alkenes. And the simple reactions we usually follow to get the epoxide is to treat the alkene with peroxyacetic acid or peroxybenzoic acid, or the known reagent that is MCPPA, metachloroperoxybenzoic acid. What happens? The oxygen that's on the terminal part of the peroxy group is going to be the one that's going to actually be the source of the epoxide moiety. Now, this cyclic ether is going to be actually useful to generate other compounds. Now, this reaction already been covered in terms of mechanism, so it's very important that you go back to the corresponding chapter and review the mechanism, being able to draw the arrow pushing and the intermediate to get to the final structure. Here's another one that's also an option to use: the magnesium monoperoxy benzoate. Magnesium monoperoxy benzoate. So that's another peroxide reagent that I can actually make an epoxide out of an alkene using it. What happens if I have two alkene units? Well, there is a selectivity. The more rich alkene will be the one that's going to be is going to go through epoxidation faster. So if I have a 2-methyl group attached, obviously this alkene will be more reactive than the left-hand side alkene. And that's why you see in the presence of MCPPA or the MMPP will actually get you the epoxide on that side of the molecule. Of course, the stereochemistry is retained. So you could see here the CH3s are already cis, so that's why they are actually cis on the final structure. Here's another example. It's a trans this time, nitrophenyl propene in the presence of MCPPA or MMP. What do I end up making? I end up making an epoxide that has the stereochemistry also retained. So the phenyl and nitro are actually trans. So that's important to keep in mind, that the epoxidation is a stereoselective reaction and a regioselective. Regioselective, that it picks the alkene that is more rich, having donating groups attached, and it picks basically the alkene to make an epoxide to have the stereochemistry in place that we started with originally. Other ways how to make epoxides other than the alkene method is to make the halohydrin, which also comes from alkene, reacting it with halogen and water. We make the chlorohydrin or the bromohydrin or the iodohydrin. That mechanism has also been covered in an earlier chapter. Make sure that you review it and remind yourself how to do the arrow pushing. Once I make the halohydrin, this structure, reacting it with a base, such as hydroxide, is going to pick this an acidic hydrogen, that's the alcohol hydrogen. And what's going to happen next is going to generate an O-. That O- will attack a carbon X to generate an epoxide. So every single time I have a structure that has an alcohol and a halogen, there is a way that I can make an epoxide out of it, or a cyclic ether. I could have not necessarily a 3-member ring cyclic ether. I could have a long, more expanded one. So that would be a cyclic ether, simply by having the OH deprotonated, make the alkoxide, and that alkoxide right away will attack the CX to make the cyclic ether structure. And it will be an SN2 pathway. SN2 pathway. Here is the whole route using cyclopentene, reacting with chlorine and water that will make the chlorohydrin. So the first step would be to make the chloronium ion. And this chloronium ion, it's a stereoselective. So you could basically make the Cl on one face or the other. And this water will attack the carbon that's more substituted. In this case, both carbons are the same, so it doesn't matter which carbon you pick. Once you do that, you're going to make the chlorohydrin. This chlorohydrin, it's a trans due to the fact that the water will attack the chloronium ion from the opposite side of the bridge. That's what we actually discussed when we covered this mechanism in an earlier chapter. So make sure that you pay attention to that you form the trans halohydrin. Once you have that, and pay attention that it's a mixture of enantiomers. So I could have the OH down and the Cl up depending on which chloronium ion I made, of course, you're going to be making both of them. And it's not a meso. So the two structures are actually enantiomers. So having one of them reacting with OH minus, what's going to happen? It's going to deprotonate the alcohol, generate an alkoxide, and that alkoxide will attack the CX to end up making an epoxide structure. That's how we generate epoxides also, in addition to epoxidation of alkenes. What do we use epoxides for? I can make useful products, one of which is something that we have done earlier, which is making an anti-diol. What's that supposed to mean? Take an epoxide, treating it with H3O+. What will happen? Oxygen will get protonated first, so you end up making a protonated epoxide. And now, having water will attack the carbon that's more substituted. Now, in this case, it doesn't matter which carbon you pick, but if there is a substituted carbon versus the other, obviously we'll pick the more substituted one because it's more electropositive. And once you do that, you're going to end up making a protonated diol, and the protonated diol will be abstracted with, basically go through a reaction with water to abstract that hydrogen to end up making the trans diol. Cis diol, out of an alkene, we use osmium tetroxide peroxide. KMNO4 dilute can also give me that, but the trans diol cannot be generated using those two methods. I will have to make the epoxide and then treat it with H3O+. What else can I do with the epoxide? Well, instead of water, I can use the alcohol as a nucleophile. So protonating it is going to give you the protonated epoxide. Reacting it with an alcohol, the alcohol will pick the carbon that's more substituted. In this case, both carbons are the same, so it will pick either one, and that will give you the protonated alkoxy alcohol, and that react with the medium or the alcohol to deprotonate, and it will end up giving you this alkoxy alcohol structure. Very similar to what we discussed earlier, the pair of enantiomers will be actually generated out of this reaction as well. Other chemistry, and this time is the base catalyzed approach. So what we discussed earlier is the acid catalyzed. So whether I make a trans diol or a trans alkoxy alcohol, that will be an acid catalyzed approach. So I pick, once again, I protonate first, and then I pick the more substituted carbon to attack it with the nucleophile. What happens if I have a base catalyzed condition, such as hydroxide, or as we're going to see later using a Grignard reagent, or an alkyl lithium. These are basic reagents. That's why we call them base catalyzed approaches. So the first one, using a hydroxide, what's going to happen? It's going to pick the less sterically hindered carbon. Now, in this case, it doesn't matter because both carbons are the same in terms of substitution. But if one carbon is more substituted than the other, this time, the base catalyzed approach, the nucleophile is going to pick the carbon that is less sterically hindered, less substituted, because you're not protonating the oxygen. So it's going to make it harder to attack the more substituted carbon, more sterically hindered. So it's going to pick the less sterically hindered carbon. And that's going to give you an O-. O- will pick basically hydrogen from water, and that will end up making the diol. So that basically is the approach if I do base catalyzed. Having an epoxide versus ether, the chemistry of epoxides will usually be faster. Why? Because epoxides are higher in energy. So in order for them to get to the open chain one, or to the epoxide opening outcome, they don't need much energy to get to there. While ethers, they will require much higher activation energy, and that's why the epoxides are actually more thermodynamically favoring the opening outcome. I can react an epoxide with HX, and the fact that I'm using a hydrohalide, I will need to protonate first, and the X- will attack the more substituted carbon. Every single time you have basically an acid catalyzed approach of epoxide opening, the nucleophile will attack the more substituted carbon. And what's going to happen next? Well, this protonated epoxide will be attacked by the halide, and that will give you basically the halohydrin. do this again with HX. This is a reaction we have seen earlier. Reacting an OH with HX will basically protonate the OH and eventually have the halide inserted. So you end up making a dihalide. So having an epoxide reacting with HX, you will end up making a dihalide. So here's an example where I have an unsymmetrical epoxide. So I have the epoxy group substituted from one end with 2-methyl and the other end is unsubstituted. So if I have the acid catalyzed alcohol reacting with this epoxide, what's going to happen? You're going to protonate the oxygen and the alcohol will attack the more substituted carbon. And that's what you see here. You're going to have actually the carbon right here with the 2-methyl going to be eventually the one that's going to have the OCH2CH3 attached to, because the acid catalyzed opening of an epoxide will always put the nucleophile on the more substituted carbon. What happens if I have ethoxide instead of ethanol H+, I have ethoxide and ethanol. No acid condition, it's a base catalyzed approach. What's going to happen? The O- will attack the less sterically hindered carbon, and that CH2 will end up the one that's going to be attached to the OCH2CH3. And in both cases, whether you attack this carbon or the other, you end up obviously making the alcohol after the epoxide opening. So this is important to keep in mind. Here is a question is asking basically what would the product be if you react this structure with sodium ethoxide and ethanol versus sulfuric acid and ethanol? Well, similar to what we discussed in the previous slide, we have an ethoxide base catalyzed. It's going to pick the carbon that is less substituted. So it's going to give you basically the OCH2CH3 on this end, and this becomes the OH as you see here. And of course, it's going to be the trans, because it's going the nucleophile is going to attack from the opposite side of the epoxy face. What happens if I have H2SO4 ethanol? Well, protonation will happen first, and the ethanol will attack the more substituted carbon because it's an acid catalyzed approach, and that will end up making basically the structure that you see in front of you here. Here's the another reaction that's a base catalyzed epoxide opening, but this time we use Grignard or alkyl lithium. What happens? No acid condition, so the nucleophile is going to attack the epoxide from the side that is less sterically hindered. So it's going to pick the CH2 side, not the CHR prime side. Then that will attack basically that carbon. You end up basically opening the epoxide and making the alcohol on the other end. And that's how we usually predict the outcome of an epoxide opening. We figure out, is it an acid catalyzed? If it's an H3O+, we make a transdiol. If it's an H+ with alcohol, we make the alkoxy alcohol, the anti-form. If I have an alkoxide reacting with an epoxy group, I will pick the carbon that is less sterically hindered. That's important to keep in mind. If I have a Grignard, we'll do the same thing. Base catalyzed will always pick the less sterically hindered carbon of the epoxide moiety. And this is the story of chapter 14.